is important to recognize that everything is going to have a graph like this that sort of describes how much it reflects the light at different wavelengths. So again, this sort of makes sense. Like that thing is a skin colored, sort of like a light skin color. It's kind of orangey, whatever. So it does, I mean, it reflects more of these like orange and red hues and not so much at the other end. And each of those graphs is basically just a big, like it's a table of data, or you can think of it as a function. But in either case, you can just multiply all those numbers together. This tells you if I were to take all of this incoming light that I put my card out in that D65 lighting environment, multiply those together, I get this is what the light looks like bouncing off of that card and coming to my eye. So this is actually sort of the result of how being emitted because it's bouncing off of that card.
I have a question.
Yes. No. In this, we're sort of not getting into directionality. The cards on the Macbeth color checker are painted with an extremely matte paint. They're designed to be almost entirely diffuse so that you don't get highlights and reflection and things like that. Because different materials, obviously, once you get into glossy materials, directionality is very important. This is very much trying to factor that out when you're doing these calculations. But good question.
An example that you can see in this room, if you look at this metal, which is very mirrory, very not matte. If you see bright highlights, meaning the individual bulbs reflecting in your eye, that's because that material really cares what angle you glance at it.
Yes.
It's not, that doesn't show the average brightness in the room. That shows a very directionally specific reflection, which is the opposite of this chart.
And just a quick note, because you might say like, well, that was like light skin, it's almost white, or or very sort of pink. Why is it all blue? But it's really, in some sense, like to think of it as almost like a warm gray, because even light skin like that, it has a little bit of an orange tint, but it's almost gray. Like it's not that far off if you were to put it on a color chart, next to the whole spectrum of things. And just to quickly compare, this is that blue sky card, and this is the reflection amounts at the different wavelengths, and sort of like you'd expect, a lot more on the blue and violet end of the spectrum. And again, we can multiply it through, putting that underneath the D65 light source, and it looks about like you'd expect. Put them next to each other. Okay, so now we know what the light bouncing off of those two cards looks like underneath that one light source. I know that this is light skin colored and this is blue. When I see that, I mean, my brain doesn't see the spectrum of light that way. That's not really what happens. This is just a bunch of energy bouncing through the air. So now we get to the biology side. And most people, not everyone, most people generally have three kinds of color receptors in their retinas. We have rods, which react sort of purely to brightness. And then we have these cones, and the cones react to three different wavelengths of light. And technically they react to a range of wavelengths, but they sort of have peaks at different areas. And they're called SM and L for short, medium, and long, which corresponds to the short wavelength, the medium wavelength, and wavelength. These are sort of normalized. The responses are not like this. So this is a graph of, for each of those kinds of cones in the eye, how much it reacts to light at different wavelengths coming in. So, the short cones really only react to a pretty narrow range of sort of blue and violet light coming in. And basically, these things get stimulated, and then they send a message to your brain, and they're like, hey, I'm seeing a bunch of stuff. So just like before, we can now take that light that's being bounced off that card, and we can multiply it by these functions, these tables of how much a cone responds to light at different wavelengths, and we can see these curves that are how much does the cone actually respond to this particular light that's being fed in.
Yeah.
Yes, that is the normalized response. That is the actual response curves are not the same height and things like that. But for graphing purposes, it makes it a little bit easier to kind of see it like this. So we have this. I mean, it's not like your brain gets this whole shape of this line. The cones basically are just getting excited by the light that's coming in, and then how excited they are is how much they transmit like to the brain. So basically, they're sort of integrating. They're measuring the area under this curve, and then they're just feeding that value back. So the cones really do just feed 3 numbers into your brain that are like, oh, there's not too much blue going on. Oh, hey, yeah, there's quite a bit of green. There is so much red right now. And that's what your brain gets. And again, just for comparison, that blue sky card after it's being reflected, very different profile once you get down here. But again, it's all boiled down into 3 numbers, which is like the area under those 3 curves. Look at them next to each other. You're like, okay, they look different numbers. And your brain is like, oh, well, that clearly looks like sky blue. And this clearly looks like light skin. I guess so. All right, so that was a lot of physics and biology. Sorry. So I'm going to tell you a little bit more about the CIE while you stare at this hopefully adorable kitten, and skim over a little bit of history. So I don't want to go over too many more charts and bore you to tears. So we could have actually made a color system, a way to describe colors using these, like the cone response function. And you can do that. There is a LMS color system that describes colors based on how much they excite the 3 different kinds of cones in the eye. But it's not super convenient to work with. The values aren't normalized, and so you get like, the range of values is different for each channel, and it's hard to describe all colors because it turns out that there are certain pure colors that you can't very easily describe that way, and it's also very subjectively based on like an individual person, so you have to average over a population anyway. So while we're doing all that, we may as well make something that's a little bit more convenient mathematically and whatnot. So there was a whole bunch of experiments done by the CIE or by some researchers that have turned into CIE data. And they said, man, it'd be really great if we could just pick some monochromatic colors like red, green, and blue, because that seems to be rough what we're dealing with. We'll pick red, green, and blue, and we'll just make all of our colors by combining pure red, pure green, and pure blue. And they used monochromatic, like pure single wavelength lights, and they had people mix them and try to recreate other colors. And then they used that data to construct an RGB color space. And they're like, oh, well, all right, we're done. We've got RGB color space. This is not the RGB color space you think of. The CIE RGB color space, unfortunately, like red has to go negative to represent certain values, certain colors that you would expect to be able to describe. So they got all done, and they compiled all their data, and they had these curves that describe the RGB color space. And like I said, you had like negative red amounts. And again, things were not normalized. And so they were like, well, that's not great either. So they said, all right, we'll take all that data and we'll do a whole bunch of math on it. A lot of math, a lot of matrix math, a lot of moving things around and normalizing and whatnot. And they produced the XYZ color space. And it is really just a mathematical transformation of the data they extracted when they built the RGB color space. And the XYZ color space has these 3 curves. And these are the actual curves. Notice they do not all go to the same peak. However, the area under each curve is the same. They all sum to 1. The XYZ color space has a whole bunch of nice properties. The values range from 0 to 1. All of the curves sum to 1. That's sort of the maximum. The other thing is that the Y curve, so these are actually backwards. This is the X value over here. This is the Y value, and this is the Z value. I think I have that right. This Y value, though, is actually the luminance. It's under standardized conditions, it represents the luminance of the thing you're looking at. Basically, how bright is that thing? And there's a sort of standard representation for that. And you're like, well, that doesn't make any sense because the Y value is like just green. that can't be right. You're making stuff up now. Your eye actually perceives green as being brighter than either red or blue at the same intensity. So if you look at a green thing at a particular amount of energy versus a red thing, the green thing looks a little bit brighter. And if you look at a blue thing at that much energy, it looks way darker. And this is like totally consistent and standardized, and everybody knows this once they hear it once from someone like me. So all of this was sort of engineered to create this situation where this curve is actually the luminance of a thing. So that means that if you have the X, Y, Z values for a color, you actually just look at the second value and you know how bright it is. What is the luminance? Oh, and then there's this other interesting thing that the X value becomes positive again down here, and this is sort of compensating. I mentioned that you needed negative red values to create certain colors when they did their RGB experiments. This is sort of adjusting for that, so they had to sort of raise the curve up and shift some stuff around. So these are sort of regions where the red would have been negative, but now it isn't. So just like we did with the cones, we can multiply through, we get descriptions, repeat that process. These are the XYZ curves, and the area under each curve are the values. These are the actual XYZ values for those light skin and blue sky colored cards underneath a D65 lighting environment. And that's it. Okay, well, that's pretty useful because XYZ, as we will find out later, is sort of one of the most universally used referenced color spaces. And a color space, a couple times, what does that mean? It's really just any way of describing, any system for describing a color. Generally a set of axes, so red, green, and blue are very common axes, but you could use cyan, yellow, and magenta, and black if you're using an inkjet printer. You could use different things to describe your colors, different kinds of values. So the XYZ color space, because it is so well specified and grounded in physics, is kind of this official, international, this is sort of ground truth for color. And then people use that to do conversions between other color spaces and to understand those color spaces. So clearly we're done. Light is just physics, and our eyes look at things. And yeah, unfortunately, we have these brains up here, and our brains are really terrible. They love to take shortcuts. The visual system is not it's not a mechanical tool for counting photons and measuring energy from light. It does all kinds of horrible things. Man, these TVs. Interesting. It does all these things to sort of help us with, avoiding getting eaten by lions and whatever else. So it's oh, that thing is in shadow. Clearly, this thing is way, way lighter than this square up here. Except it's not. They're actually the exact same color. I've seen this illusion dozens of times, and every time I look at it, I'm nope, it's not true. And then I look at it again, I'm yes, it is. I've verified it. Makes me sad. Makes me sad that my brain can't fix that. So yeah, we have a lot of bugs in our visual system, if you want to think of it that way. Too many late nights coding that didn't quite didn't get everything ironed out there, I guess. So I mean, this is sort of a pure grayscale image, and you're all right, so yeah, you're not very good at judging brightness, but it affects color too. Our color vision is very heavily affected by things like the lighting environment and assumptions about the lighting environment. When we look at something, we say, here it's we're assuming that thing is in shadow because we happen to draw a big green cylinder here and make it look like there's a shadow. So that affects how we perceive it, and it affects how we perceive color too. I'm just curious, does anybody in this room see that as blue and black right now?
Blue and black.
Yes. Yes. And I'm guessing a bunch of other people see it as white and gold. Yeah, okay. And then there's some people that can make it switch back and forth. So this came about a couple of years ago. You've probably already seen it. It's this picture of a dress that somebody took, and they threw it up on the web, and then they were oh, my friends and I can't agree on what color this is. And then it turned into this huge thing, and now there's people doing studies about it because it turns out that 57% of people see this picture and think the dress is blue and black. And then another 30% think it's white and gold, and I'm one of those. And why? Well, there's all these subtle cues in this picture that the lighting in this shot is completely absurd. And it was taken with a flash, at noon on bright sunny day or something. I mean, totally washed out, ridiculous colors. But apparently some people's brains are I need to subtract all of that lighting environment from this picture. And then when they do, they're well, this is blue and this is black. And other people are yeah, the lighting's pretty bad, but this is white and this is gold. So there's studies going on now about how this happens because, all right, well, that means that we've clearly lost because if we can't even agree on what color this thing is, then there's not much we can do. Game over. Not necessarily. There's under better environments and better conditions, we can do a lot better than this. I think this example in particular is really just an argument for consistent and predictable lighting. Don't take pictures under absurd lighting environments, and hopefully you won't run into this. And that's sort of out of the scope of this talk, but sure. All right. That's an awful lot of depressing stuff about how bad we are at seeing color. I am now done with all the theoretical. So clearly we want to enter hex values and get some nice colors on the screen. And like I said, I told you, this is red and this is green and this is blue. So we're using some kind of RGB representation of color. I guess it's not XYZ. It's definitely not CIE RGB because I don't think I've ever entered a negative number for red. All right. So I guess that's some other definition, but we'll assume that we know what we're talking about. And we've got red, green, and blue values. Based on everything I just told you about how light works and how all these color systems are based on measuring the area under curves that react to light, clearly those red, green, and blue values are and how much green energy and how much blue energy, right? No, not. And that's where we get to gamma. So gamma is, I guess I would call it the first big mistake that everybody makes when they deal with color for the first time. Generally, those values that we're dealing with, those RGB numbers from 0 to 255, are not linear in the sense that they represent how much light there is. And now we're going to really be putting this monitor to the test. I've already tried some of my demos up here, and I know they're not going to work, so I apologize. So there are two gradients here that go from white to black. This top gradient is, if you were to just draw a gradient in Skia today or in your web browser with whatever tool you're using, pretty much any program, even Photoshop out of the box, you will get that first gradient. Except that that's not actually linear in the amount of light that's being emitted. Like if I go to the halfway point, this little middle area here, it's not half as much light or half as much white, light energy as I get over here. And why is that? Why do we settle for that? Gamma goes back to CRT monitors originally and how they had this sort of nonlinear response to the voltage you applied and how much light was emitted. All of that is true, but it's also basically irrelevant at this point. At this point, all that really matters is the human visual system also has a very nonlinear response to light. We are much more sensitive to changes in relative brightness in dark areas than we are in light areas. So down here, we can do a really good job of distinguishing all the different shades of black and gray down here. Once we get up to the high end, we're I don't know. I mean, after it's mostly bright, a little bit more bright, we're it's all the same. This down here is actually linear in the sense of how much light is being emitted. And you can sort of see that. Around about here, I'm whatever, it's white. Why are you still doing this? The interesting thing is that this is partially sensitive to the background of the image. It actually gets better if I do this. Again, because of contrast and your eye is sort of adapting to cues around the gradients. It's pretty, this looks pretty smooth, not smooth, but at least uniformly changing versus this one that looks a little bit different. So what is that? What's going on there? And now we're going to attempt to do something else, and we'll see what happens. All right. Brave enough to try to do this live. We'll see how this goes. So I mentioned we have this sort of nonlinear response. Our eyes are much more sensitive to changes in light in dark areas than they are in light areas. And it's sort of like an exponential curve, which is what people typically think of as the gamma curve. That is a description of how the values that we use, those red, green, and blue values, map to the actual luminance, the actual brightness of things on the screen, or coming out of the light source or whatever. So the most common curve that is used nowadays on most people's monitors and everything else is this sRGB curve. And it looks just sort of like a little parabola guy, and it goes from 0 at the bottom up to like 1 up top. But it's definitely not linear. It's kind of a little bit different. People sometimes will talk about the gamma value, and they'll just give you a number. They'll be like, oh, it's gamma 2.2. Gamma 2.2 is very common, and that's basically the exponent in the curve. So if I go here, I do this, barely see it because they're almost exactly the same curve. This is actually the 2.2 gamma curve. And what this means is this x-axis is basically the value in your color that you're talking about. So you say like, 7F, which is like 128 or something. So that's like 0.5. If we come here and we look at like 0.5, we see that that's only like 0.21 or something. So that value, that Y value, is actually how bright that is relative to the normalized scale, which means that if you're doing math on colors, you really want to be doing math on values that are linear, that represent how much light energy there is. Because if you don't, you're sort of doing math along this weird curve, and things break down. And I'm going to try to show that to you, but those are a bunch of the demos that are not going to work. We'll see. So why have we been doing it wrong? Because we have been doing it wrong. Everyone's been doing it wrong for a long time. Game sort of transitioned and tried to fix this years ago, but a lot of people still are incorrect. The main reason is speed. It's a lot easier. If I give you like two numbers, 100 and 127, and I tell you to add them together to, put something on the screen, you're just going to say 227 because that's a lot simpler than raising one of them to the 2.2 power and then adding the results and then undoing that with the inverse, which is basically raising them to the 0.45 power along this other curve. So you're like, I don't want to do any of that. I'm not going to. Computers are slow. Turns out computers have gotten faster, so we can do this. This sRGB curve that I showed you originally is almost a 2.2 curve, except it has this little tiny bit at the bottom. It's a flat line at a slope. And then it has a different exponent to kind of catch up to the 2.2. End result is they're basically the same curve within a very tiny margin of error. So try to switch back here. So I mentioned you really want to be doing math on values that are linear, not these sort of like gamma values that are on this weird curve. Why is that? So here's a different gradient. Sorry, that looks better. Good. And again, this top one is sort of what you get if you just do a gradient from pure red to pure green in most applications. This bottom one is what you do if you take the gamma into account. You convert these values into linear values. You blend from in sort of linear values of how much red light there is and how much green light, and then you convert back into that sort of sRGB gamma curve so that when you put it on the monitor, it looks right. Because on the monitor, you want to be showing values that are on that curve because our eyes have that same sort of nonlinear response, and they are sort of tuned. Everything is expecting that you will get values along that curve, and it will perceptually be linear to you. It's a little confusing. The important point is whenever you want to do math, you really want to take your values, make sure you turn them into linear values, do your math, and then turn them back. that's what I've been doing for the last couple months. That's what I'm going to keep doing, so that hopefully there isn't too much that has to be done by anybody else. The browser and everything else will just do it. So here you can kind of see, you get this very like muddy brown in the middle versus getting a nice sort of yellow that you would expect if you were to do this. And sort of as a rule, whenever you do math in gamma space without converting to linear and back, things get darker. Like always, things get darker. If you're scaling an image, if you are doing a gradient, no matter what you're doing, everything ends up darker than it should be. Just to sort of explain why, again, if I had, imagine a checkerboard that was all black and white, and I wanted to average that, you would expect it to be half as bright as the pure white parts of the checkerboard when I look at the sort of average scaled version of that. But if I take a black pixel that's, you know, got 0 as its value, and that maps to 0, a pixel that's at 1, and I average them together, and I don't do the gamma math, I just naively add them, I produce a value of like 0.5. But again, that's only like 21% as bright as the original sort of pure white. So I needed to sort of correct for that. And the corrected value was like way up here to get a Y value of 0.74. So, all right. So one example of things looking a little bit better when you do your math correctly. Now we're going to show some things that, man, I don't think are going to work. We shall see. Worst case, I'm going to force you to look at on laptop screen where they will look correct.
So, by the way, the reason it's likely to gonna not work on that TV is because the hardware that is sending the video from his laptop to the giant screen is taking the same shortcuts that he's complaining that
Yes.
we do. The hardware is also saying, oh, I have to scale an image from a laptop. It does the math quick and dirty, and the image on the monitor is going to be dark.
Yes.
And this is, so even the demo is demonstrating that it gets in the way of you seeing.
Yeah. So, and already you can tell something is wrong here because this is in fact like a checkerboard of individual pixels, individual red and green pixels. And there's like this weird patterning. So clearly something has gone wrong along the way. And in fact, I'm pretty sure the TV, despite all of my best efforts, is stretching or squishing the image slightly. And when it does it, it is ruining that, which ruins the effect. So I'm going to see. I apologize now for how tough this is going to be.
Actually, it only takes us a moment. I bet people can walk up and your laptop.
Yeah.
If it doesn't work.
So let me compare the two. I will show this up here quickly and explain what you're looking at, and then I will show it on the screen that is not doing bad things. Basically, like I said, this is a checkerboard of pure red and pure green. So if you were to look at that, you would picture that is the sort of half red and half green. Like that should be what I get if I take those two colors and add them together and average them. Like that is the result. Think of it as like a screen door, you know, that you're using to filter out half, and then you add on the other one, and like that's what you should get. This is a Skia application, and we let you run things sort of doing the math correctly or not. And this over here is like a pure red square in the background. This is a pure green, but it's at 50% alpha, so it's sort of only half pure green. And if I drop that on top, now if the screen was working correctly, this would be a whole lot brighter than this. And if I drop it down on my laptop screen, it will be. Until, of course, I switch on the gamma correct flag, and then we will do all the math the way we expect. It's probably hard to see. You might even be able to catch it if you squint right now. So this is like quite a bit brighter than that overlay patch right there. If I turn on the gamma correction, the green itself gets brighter against the black, and the actual overlay patch now actually matches that dither pattern, which again, is what you want to have happen. I mean, that's the idea. So, and again, this is why this is hard. Even, you notice I'm running my laptop at like ridiculous resolution here, like I can't read the text. That's because, again, if I set the laptop to a smaller resolution, Windows scales the screen incorrectly and does the wrong thing with gamma, and the image is wrong. Everybody is wrong is the moral of this story. This one, I don't know. I tried to show this up here. We will see what happens. So, anti-aliasing. Oh, my Zoom thingy is.
It's just off the bottom.
It's way off the bottom, yeah. Trying to make the window
Shrink the
smaller.
window, yeah.
There we go. So we're drawing a sort of convex shape with Skia, and it's just black and white, really simple case. And we do this nice anti-aliasing. We get the edge, we kind of filter it to make it look smooth when you look at it from a distance, so it doesn't look all hard and jagged. So we do this. The problem is if you do that without taking the gamma into account, the anti-aliasing also looks worse. Even though, I mean, this looks nice and smooth and it's hard to tell that that's wrong, if this were on my laptop screen, weird, like bouncy look because the steps are not even. And then this is hard because the resolution of the screen is so high. But it does, in fact, get better. You'll have to trust me. It gets significantly better. Mike discovered this by accident, I think, like 2 days ago, how much better the anti-aliasing on our images look. So that is pretty much the gamma side of things. Is we really need to be careful whenever we are doing math, whenever we are, and that includes, like I said, rescaling images. Because again, if I stretch an image and every time I need to like generate a new value in between, or every time I like make a thumbnail and squash it down, every time I need to average those values and generate a new value in the middle, if I don't correct for that, everything gets darker and darker and darker. And that's not what we want. We want to preserve the values as much as possible. So we are, what I've been working on is making sure that we have a way in Skia to do all of this math the way we want to and account for all of this. So now we've done all of our math. Everything is linear. We are done. We have red, green, and blue values. We know they're not actual like amounts of light. We're finished. Not quite. Now I hand it over to Matt, and he tells you the other half of the story. All right. This is like so weird. So Matt, you want to talk about gamma?
Sure, yeah.
Because now we still need to know what those red, green, and blue values represent.
Yeah, so I guess Brian described gamma as the first big problem color on in graphics. I think I would describe gamut as the second big problem. Brian's already introduced the uniform XYZ space that allows us to represent all of the colors that humans can see. So it might be tempting to think, well, all of our images and all of our monitors, they should think about colors in terms of that XYZ space. And there's a number of reasons why they don't, but one of the biggest reasons is gamut. Images and monitors and phone screens, all of those have a gamut. And all a gamut is it's a description of the subset of all the colors that monitor understands and can represent accurately. So I'm going to do a really quick aside and make everybody learn one more color space, the XYY color space. It's really, really closely related to XYZ. You just do a little bit of math to go from XYZ to XYY. And the advantage of going to XYY is that I can graph all of the colors and show them in a nice 2D representation, which I think makes you visualize gamut. If you're wondering where the extra dimension went, that's the capital Y, which is luminance or brightness. And we're not graphing that. The XY that we've graphed is kind of a slice of the plane. And if we had different slices, it would be darker or brighter versions of those colors. But theoretically, in that slice that I'm showing there, we're showing in 2D all of the colors at a specific brightness. But are we actually looking at all of the colors? The answer to that is no, because this monitor has limitations. As I've said, it has a gamut. It can only represent so many colors of all of the colors that humans are able to see. And similarly, however this image is encoded, it's only encoding a representation of the colors that it understands. So just to give you an example of some common gamuts, a good way to define a gamut is by 3 points on this plane, where we say this is the reddest red that this monitor can represent, this is the greenest green, and this is the bluest blue. And then we can kind of show the gamut in a triangle, where a bigger triangle means that we can represent a wider range of colors, and a smaller triangle means that we can represent a smaller range of colors. And there's an endless number of gamuts. We could just go home and pick 3 points and make our own gamut. So why does all of this matter? Well, here's an image that I've chosen, and let's show 2 different renderings of that image. One where we're pretending to be on an sRGB monitor, where the gamut of the pixels is interpreted to be sRGB, and the other version where the pixels are interpreted as being in an Adobe RGB. Adobe RGB gamut is bigger, which means we can represent a wider range of colors, so the colors look more intense. For example, if you have a pixel that's 50% red, or half the red is turned on, since Adobe RGB can represent a more vivid red, a 50% red pixel in Adobe RGB looks redder. So now we have this problem. We have 2 different screens representing the same image differently. And 1, we want to know which is right. And 2, we probably just want to be consistent. And the answer to which is correct in this case, we actually don't know without having some information from the image saying, hey, all my pixel values are meant to be interpreted in an sRGB gamut, or hey, all my pixel values are meant to be interpreted as Adobe RGB. And I meant to say this earlier. I know Brian talked a little bit about sRGB gamma, and now we're talking about sRGB gamut. And I don't want to confuse you about that. sRGB is a color space, and to define a color space, you need a gamma and a gamut. So sRGB has both of those. I'm talking about the gamut now.
There are other color spaces with different gamuts that still use the sRGB gamma.
Yes, the sRGB gamma is fairly standard. So, and gamut is not just an issue with images, but it's also an issue with blends or any of the kind of cool graphic stuff that you might want to do. I've decided to show a blend of red with red, which is very, go ahead, Jim. I have no idea. I cheated so it would look right. But good question. Yeah, this is, I kind of had similar issues to Brian, where the unpredictability of how the connection to the screen and how the screen was going to interpret colors made some of the demos to ensure that it looked right be a little bit interesting. So back to why am I showing us a blend of red and red? The reason I'm doing that is because we can be, right answer should be a red patch that looks exactly the same as those 2 reds. But what's interesting about this blend is I'm going to do what graphics engines have been doing for a long time and just close my eyes and assume everything is in the same gamut when we do the blend. But we'll realize that if we make that assumption and that's actually not the case, the blend will turn out wrong. So this image on the left is a red patch, which is the max red in the sRGB gamut. So if you look at a pixel, red is 255, it's maxed out. Everything else is 0, it's maximum red. The image on the right, while it looks exactly the same, that image is we should interpret that in an Adobe RGB gamut, which means that to get a matching red with sRGB, we only need 218 out of 255, not quite max red in the Adobe RGB gamut, red in sRGB. So the pixels on the right are really 218 red, everything else 0. But because we're interpreting the gamma as Adobe RGB, they look the same. So what happens if we blend these two patches? Well, what we do now is we would just do an average of the pixels. So we would end up with pixels where 37, or I can't remember what the value is, some red value that's not quite max in 0 of the other values. So my first question is, when we get that red, should we interpret that as sRGB or Adobe RGB? I don't know. Either one is, we're already doing something wrong. Either one is wrong. Let's say we choose sRGB. Well, if we choose sRGB, the result looks darker than it should, because 237 in sRGB red is not as bright of a red as the max red. So by doing the blend and not taking gamma into account, we've gotten the darker, we've gotten the wrong result. If we interpret as Adobe RGB, well, if we're on a screen that can represent Adobe RGB, the red's gotten more vivid. If we're not, we have to make a decision about how to deal with a red that's too bright to be represented on the screen. And that's a whole other question that I'll get to in a little bit. So the good news is that the XYZ standard, which Brian introduced, is awesome because it's given us a uniform way to think about colors and look about colors in a gamut that everybody understands. So we can solve the problem that I showed with the images and also the problem that I showed with the blending just by understanding the gamut and making sure that we're either in the same gamut or in a gamut that we understand. So this is just a quick possible workflow where we have an image, but encoded with the image is some sort of profile which says this is the gamut, this is how you should interpret my colors. So then we can do a transformation into that profile. The way that's defined, the way you define your colors is just you say this is how you transform my colors into XYZ, because everybody understands what XYZ is. Use that profile, we transform to XYZ, and similarly, a monitor or device will have a profile that says this is how you transform from the colors that I understand to the XYZ colors that everybody understands. So by taking advantage of those profiles and using them, we can actually begin to become more color correct. And that's one of the challenges that we're working on right now. So are there any potential problems with this system, or is everything okay now that we've started looking at gamuts and doing the transformations? Well, it turns out that there is one potential issue, and that is dealing with mismatches between gamuts, particularly.
So we're going to start the final panel in here now. So people who would like to come see that, we'll move to Google.
Thank you, color.